SwayamPrabha. Digital India. Educated India.
Okay, so let us continue our discussion with respect to the this particular course. And in the previous module, okay, one last problem we solved. In that you have to note down a small change here. So this particular problem Q2 we solved in the previous one. Okay, previous module. You will see that we calculated epsilon 1 and then we calculated blank holding force B, isn't it? So this B is actually in kilonewton. We missed it. It was kept as Newton. So you have to be a little bit careful in units. This is to be in kilonewton. So that change you basically note down. Okay. So so now we are going to start discussing about the next module in mechanics of sheet metal forming. Okay, that is basically your load instability and tearing. Okay, so load instability and tearing. So this particular situation, load instability and tearing comes. Okay, so when you deform a sheet beyond uniform plastic deformation. So we start with zero deformation and then we cross elastic portion, we enter into plastic deformation. Okay, so and so wherever the transit happens, you are going to have the significance or use of yield locus or yield surface to know the onset of plasticity. Then we have a very nice uniform plastic deformation in the strain hardening region described by any power law we have used. Okay, and then we are going to reach a deformation stage where instability is going to start. Okay, so when we say instability and tearing in this particular course, it means that the material is actually going to fail. The material is actually going to physically fail. Okay, so beyond yielding, beyond plastic deformation, we crossed the entire uniform plastic deformation, and then we are going to reach, let us say for example, closer to UTS, and that is where your instability is going to start. And after that, if you deform, it will convert into full fracture. So that is the situation. So we are going to call this as load instability and tearing. So instability can be of variety of types. So I have just noted here a few of them. So one is when the load reaches a maximum, the deformation will concentrate on a particular region and diffused neck will be generated. Okay, the uniform deformation is limited by this load, that is P max, after which deformation is going to be non-uniform. Okay, so we are going to reach a maximum load, that is nothing but your P max. Okay, in the load displacement graph you can imagine. Okay, we are going to reach P max. Okay, and you will see that once you reach that particular stage, we are going to have diffused necking. Diffused necking means the neck is generated over a larger gauge length, larger span. Okay, in the gauge region, that is called diffuse neck. Okay, and the moment this happens, you will have your uniform deformation is going to cease. Okay, and after which what you are going to have is a non-uniform deformation that we already discussed in the first section. Now this is a diffuse necking. You can also have localized necking. Okay, so localized necking means what? Localized necking could be next stage of diffuse necking. Okay, in which there is a neck that is basically constricted in a small region. Okay, very small gauge region. You will see this neck, and this could suddenly happen. Okay, and this can quickly cause tearing and full fracture. Okay, this is a form of local instability. Local instability means in outside this region you are going to have, you may not be able to find any such information, but then locally it will create some sort of instability in a small section of gauge length or material. Okay, and if you want to analyze more on this aspect, you can concentrate only on that location and not necessarily the other locations in the material. Okay. For example, tensile test. And after this localized necking, you will see that the material is going to fracture fully. Okay. So, since the material that we are going to discuss are of ductile nature, so you will have a fracture after sufficient amount of uniform deformation, and brittle fracture type of material we are not going to consider at all in this course, because you are not going to make any useful component, sheet component from that. Okay. So, that is what I have written here. So, how do you quantify fracture? Okay. How do you quantify necking? So, all these things will have some theoretical basis. That is what we are going to see. Other than this, you are going to have something called as wrinkling. Okay. So, wrinkling, you know that it is going to, suppose like for example, in a deep drawn product, in a deep drawn cup. So, you will see that wrinkling is going to happen on the flange region of the cup, and that could be because of compressive nature of one of the principal stresses. Okay. It is like buckling. Okay. It is like buckling of a column. No? Okay. Similarly, you are going to have wrinkling of the sheet, okay, away from the its own plane. Okay. So, that waviness, okay, it could be because of this. So, instability can be of variety of types depending on what metal forming problems you have. With respect to sheet metal forming, some of these are described in this particular slide. Okay. So, now we will discuss one after another how we are going to quantify instability. And when we speak about load instability, what do you mean by load instability? Means instability we are going to describe in terms of load requirement. We are going to put some condition for load requirement. Okay, when instability is going to happen, okay, a load is going to satisfy this particular condition, and then we keep on deriving some equation. Finally, it lead to a very useful equation through which you can predict appearance of neck during deformation. So, the first section that we are going to pick up is basically uniaxial tension of a perfect strip. Okay, uniaxial tension of a perfect strip. So, perfect strip means sheet. You can say per strip means sheet. Okay. So, when we say sheet, it could be of any dimension, but then when we speak about strip, we are speaking about like for example a tensile strip. Okay, and we are going to pick up the gauge region, which is typically a rectangular shape, isn't it? So, you have a tensile strip, okay, with the gauge region like this, right. So, you have a tensile strip like this, okay, and this is your shoulder region, okay, which has got a particular thickness. The sheet will have particular thickness, right. Sheet will have particular thickness T naught, let us say. Okay. So, we are going to pick up a gauge region, okay, for example like this, let us say L naught, and this is, we are going to call it as strip. Okay. So, you can also call it as sheet, but you have to be a little bit careful with respect to how you imagine the dimension. Okay. So, what is perfect strip here? We will see that. What is perfect? What is the meaning of perfect? We will see in due course, and how this perfect strip looks like is given in this particular figure. You will see that this is nothing but a gauge region with length L and width W, which has got a thickness T. Okay, and this will have a uniform cross section area, let us say A or A naught. Okay, it will have uniform cross section area, let us say A or A naught. Okay, and you are going to displace the material, and there will be a corresponding load required with respect to displacement. Okay, so now what we are saying is, when this strip is stretched in tension, okay, the volume remains constant, we know, due to plastic deformation, and the following equations apply. Cross sectional area is given by A is equal to your W into T. Okay, A is nothing but WT. Okay, where W is the width of the strip and T is the strip thickness, and volume remains same. Okay, at any instantaneous deformation stage, you will have AL, which is equal to A naught L naught. Okay, so these two will remain same, and from this you can get the relationship between the new area of cross section A and the original volume, where N is the final length and L naught is the initial length. You can say instantaneous length also. Okay. So, now what I am going to do, I am going to differentiate this equation to get this particular equation, dA by A plus dL by L will be equal to 0, or I can also say that dL by L, which is nothing but d epsilon 1, which is nothing but minus of dA by A. Right. So, as per original definition of strain increment, dA is nothing but dL by L. Okay, this we discussed in the probably in the second module, and you will see that dA by A is equal to minus dL by L. So, which is nothing but you are going to have minus here. So d epsilon 1 is equal to minus dA by A, which is equal to dl by L. Okay. So now from this you can get epsilon 1 as ln of L by L naught. This is the original definition of your the principal strain epsilon 1 L by L naught. So ln of L by L naught, new length divided by the original gauge length. And since it is a tension test, okay, the state of stress is given here. So you are going to have only sigma 1, 2 and 3 are not there until instability starts. So sigma 1 is nothing but you can write it as P by A, and A is nothing but A naught L naught by L. So A naught L naught will be the denominator. So it will be PL by A naught L naught. Okay. So with this basic description, what we are going to do is we are going to put a condition that when the load reaches maximum, okay, for example, you draw a graph between load versus displacement, it reaches a maximum load. Okay, let us say it is a P max. When load reaches maximum P max, we are going to say that dP is equal to 0. We are going to say dP is equal to 0. This is the condition for instability. Okay, this is a condition for instability, we can say. So at maximum load dP is equal to 0. This can also be written as d sigma 1 by sigma 1 plus dA by A. Why? Because P is a function of sigma 1 and A. So you can say d sigma 1 by sigma 1 plus dA by A, which is equal to 0. Okay, and you can also rewrite this as d sigma 1 by sigma 1 dA by A is nothing but minus d epsilon 1 is equal to 0. Okay, so dP is equal to 0 or d sigma 1 by sigma 1 minus d epsilon 1 equal to 0. So this can also be written as 1 by sigma 1 d sigma 1 by d epsilon is equal to 1. Right, 1 by sigma 1 d sigma 1 by d epsilon 1 will be equal to 1. Okay, this is an important condition for us to give some idea about when instability is going to start or when maximum load is reached. So when maximum load is reached, okay, when you reach P as P max, then this fellow will be satisfied. 1 by sigma 1 d sigma 1 by d epsilon 1 will be equal to 1. Okay, so this equation on the left hand side, it is actually called as a non-dimensional strain hardening parameter. Okay, non-dimensional strain hardening parameter, and you can get these values from a true stress strain data, right? So load versus displacement graph will give you true stress strain data, right? So our typical curve like this. Okay, and what you need to get is actually d sigma 1 by d epsilon 1. So at every point in the deforming zone, you have to get this particular ratio and divided by the sigma 1. Okay, and you can plot that with respect to epsilon 1. Okay, you can plot that with respect to epsilon 1. So you will get this particular data. Okay, and we are going to say that this is the condition for maximum load, and this is also called as considered condition for maximum load in a tensile strip. Okay, so when maximum load is reached, this condition is going to be satisfied. Okay, so we are not going to stop with this. Now what we are going to do is any further evaluation depends on what kind of material law you choose for the sigma 1. Right, so our standard equation, power law equation is sigma 1 is equal to k epsilon 1 power n. Okay, if we choose that particular strain hardening law, okay, sigma 1 is equal to k epsilon 1 power n, if we choose that, then what will happen is 1 by sigma 1 d sigma 1 by d epsilon 1. So 1 by sigma 1 will remain, d sigma 1 by d epsilon 1, you can differentiate this, and finally you will get that it is nothing but n by epsilon 1, n by epsilon 1. Okay, so just before we make a conclusion from this, we will get one more equation which is already introduced to you in the previous modules. Before we get that, this particular situation, okay, can be described by this particular graph which I was just explaining from this particular one, isn't it? So you draw a graph between 1 by sigma 1 d sigma 1 and d epsilon 1 with respect to epsilon 1. If you plot that, you will see this particular left hand side of that equation will actually decay or decrease in this manner, Okay, so there will be one particular location where this fellow is going to be equal to 1, and if you draw a horizontal line and if you come and meet here in x-axis, epsilon 1 will be equal to one particular value, and that value can be obtained by further derivation. So what is that? So 1 by sigma 1 d sigma by d epsilon 1 is equal to n by epsilon 1, and in the previous equation you will see that it is 1 by sigma 1 d sigma 1 d epsilon 1 is equal to 1. So these two equations can be equated, and I am going to say that 1 by sigma 1 d sigma 1 d epsilon 1 would be equal to n by epsilon 1, that will be equal to 1. So I can say that n is equal to epsilon 1, and since I am going to put a condition for maximum load, I am going to call this as epsilon 1 star, which is the same epsilon 1 star which we introduced in the previous module. Okay. So there also we got I think n by, we had a general equation, no? I think epsilon 1 star is equal to n by 1 plus beta we introduced, and then if you choose pre-strain, in place of this equation, if you also include pre-strain in this equation, then this equation got changed. I think n minus, there is a factor of pre-strain into it, and when pre-strain is not there, it becomes n, that we discussed in the previous model. So here also we are going to introduce a similar equation we derived in this fashion, that is epsilon 1 star equal to n, and here actually that star indicates maximum load condition, or epsilon 1 star is nothing but limit strain only when you discuss in terms of tensile instability, and this is a condition for diffuse necking in a tensile strip. This is a condition for tensile diffuse necking in a tensile strip. So now when this fellow is equal to 1, you draw a horizontal line, it will meet x axis, and you will see that the epsilon 1 will be equal to n as per this particular equation. Okay. So when you do tensile test, get true stress strain data and get this particular data, and you plot that with respect to epsilon 1, you will get this particular similar graph like this, and whenever this becomes 1, you will see that epsilon 1 will be equal to n. Okay. If the instability is going to happen for a condition dp is equal to 0. Only if that happens, then these all equations are valid. Okay. So instability condition for tensile strip, if you want, then you can tell these two conditions, 1 by sigma 1 d sigma 1 d epsilon 1 is equal to 1, or if you follow the power hardening law, sigma 1 is equal to k epsilon power n, then you can say epsilon 1 star is equal to n. Okay. Or two equations that describe the condition for diffuse neck in a tensile strip. Okay. So now what we are going to do is, we are going to introduce the term imperfect or perfect strip. We introduced here perfect strip, isn't it? So what do you mean by perfect strip? Perfect strip basically means it is not a real strip. It is not a real strip. So where is the question of real strip? What do you mean by real strip? Real strip means it's a strip which you actually see in practice, okay, like what we do in experiments, like tensile samples with a lot of heterogeneity in the material, geometric heterogeneity in the material, like that. So that's a real sample. Okay. But if you really look into this type of gauge region which we have picked up and analyzed, you will see that the entire strip is actually perfect. There is no defect available in this material. Okay. There is no defect. It is not defective at all. Okay. So it is actually not a real strip. It is actually a perfect strip. Real strips are actually imperfect strips. Okay. Either we use real strip or imperfect strip, and opposite to that is a perfect strip, like what we see here, like what we have seen here. Okay. So that's why I have written, unlike in a real strip, okay, real strip means like what we witness in actual tensile test experiments, because it is a perfect strip, we are going to say that necking will not happen at all. So diffuse necking cannot occur in all the elements, okay, in the perfect strip. Why? Because it will behave in a similar fashion and uniform deformation will continue to occur. Right. If it is a perfect strip, okay, then there is no location which is actually considered weak. If that is the case, then all the elements in the deforming zone, okay, for example, you pick up these elements. So there could be a number of elements, you can discretize that. All the elements in this strip will behave in identical fashion because it is perfect one. Okay, it is not a real one. Then your diffuse necking will not happen at all and uniform deformation will continue to occur. Okay. In that case, you can describe your load by a simple equation, P is equal to sigma 1 into A, which we already know. Sigma 1 is nothing but K epsilon bar power n, 1 power n, and A is nothing but A naught L naught by L. And A is nothing but instantaneous area of cross section is nothing but A naught L naught by L, and this is nothing but K A naught epsilon 1 power n. This L by L naught is nothing but exponential minus epsilon 1. Exponential minus epsilon 1. So what does that mean? That means you can draw a graph between P and epsilon 1. Okay. Why? Because A is a material parameter, N is also material parameter, they are constant values, and A naught is the initial area of cross section, which is also constant. So, only variable is epsilon 1, okay. And you will see that this kind of equation, theoretical equation, will give you load versus strain graph in this format, in this way, okay. So, this equation will give load versus strain graph for a perfect strip, okay. Load to deform a perfect strip obeying our power law, standard power law k epsilon power n is given by this equation, and if you follow this equation you will get a load versus strain graph like this. So, it will start going like this and it will continue to go like this, the red color one, okay, the red color portion, the red color curve, okay. But if you want to compare this with respect to real strip means like what we do in experiments, okay, the real strip which are actually imperfect in nature, okay, then you will see that there will be a good difference between the load reduction and the displacement at which full fracture is going to happen, the strain at which full fracture is going to happen, okay. The difference is given here, you can see that. So, what is the main difference? In main difference is in real strip the load actually falls off pretty rapidly, okay, when compared to the perfect strip. Why? Because a load is not going to come down so easily in perfect strip because the material is actually perfect without any defects, but in real strip there are going to be defects quite naturally, okay, and hence there will be different locations going to undergo different levels of strain. There will be one weaker region which is actually going to govern the further instability process, and you will have a sudden drop in load once your P max is reached, which is what is shown here. So, variation in load in real strip and perfect strip is not same. In real strip, after reaching maximum load, the load falls off rapidly, while this is not so in the case of a perfect strip. Okay, you can see there is some small decrease, but then it is very gradual. Okay, what does that mean? That means this indicates that we need to include an imperfection in the strip and develop theoretical models for load instability. Or if you want to calculate, let us say epsilon 1 star, you can say, right. So, if you want to actually calculate for the real strip, okay, which is going to have imperfection, then you have to really put some theoretical imperfection in the strip for further analysis. Okay. So, that is why I mentioned very clearly that you are going to have uniform area of cross section A here, uniform area of cross section A here. Okay. So, now this is the situation with respect to your perfect strip. Okay. So, now we are going to convert this perfect strip into imperfect strip by including some imperfection in the strip, and how are we going to consider it is given in this particular section. So, what is given here? There is a figure here, you can understand this. Okay. So, this figure is nothing but again a gauge region, okay, in a tensile strip you can imagine. Okay. Only thing is like we are going to introduce an imperfection here. The gray region which I introduced here has got an imperfection. Okay. That is why I given here as imperfection. And the outside region, the colored one, is actually a uniform region which is similar to the previous sample which you have seen. Okay. So, as usual you are going to get some load, okay, with respect to strain. You can plot for this particular sample, and from the thickness direction point of view you can see that okay, what is the difference between imperfect region, uniform region is basically in the imperfect region you have a small change in thickness as compared to your uniform region, and that will lead to change in area of cross section. Here if it is A, here it is A plus dA. If it is sigma 1, it is sigma 1 plus d epsilon 1. Here it is epsilon 1, it is epsilon 1 plus d epsilon 1. Okay. So, that is why I have written here it is an imperfect strip equivalent to real test piece in experiments. So, whatever defect you have in the real test piece, you are going to have an equivalent imperfection, that is called your thickness imperfection, like this. Okay. So, if the thickness here is, let us say T, okay, here is going to be slightly less than this particular T. Okay. Actually, this dA actually is going to be a negative quantity. Okay. So, suppose this thickness is, let us say 2 mm, which we 1.2 mm, 2 mm, 0.8 mm, like that. Okay. Then you can see that the thickness in this region could be, let us say 1.999 mm, something like that. Okay. 1.999 mm, something like that. So, there is a small imperfection here, that is the meaning. Okay. So, now once we introduce this imperfection, now it is equivalent to a real test piece, a real strip. So, and we are going to now further put some discussion on this, derivation on this. What we are going to do, we will see it now. Okay, so now for simplicity of analysis, we are saying that this imperfect region, okay, is actually perpendicular to the loading axis, isn't it? So, it is easy to understand. Okay. So, I have written here that the imperfection, okay, is characterized by slight lesser cross sectional area. Okay. The initial area of most of the strip is A naught, or you can say A. Okay, either way is fine. So, you can take it as A naught also. That means the uniform region, it is A naught. Then imperfection is initially of area A naught plus D A naught, where D A naught is a small negative quantity. Okay. You can call this as A naught also. It's okay. It is going to refer original area of cross section, nothing else. Okay. So, if this is A naught, this is going to be in this region, it is A naught plus D A naught. Okay. So, now how do you calculate load for this particular situation? Okay. The load is going to act, okay, perpendicular to this, and these two regions, okay, this uniform region you can combine one as one, and this is another one. These two regions are connected in this fashion. Then you can say that load transmitted in these two regions could be equal. So, you can say P is equal to, so this fellow is actually for uniform region, and this fellow is actually for imperfect region. So, the same equation which we wrote before, okay, sigma 1 into your A. So, then you can rewrite this as K A naught epsilon 1 power n exponential minus epsilon 1 is equal to K. Instead of A naught, you are going to refer A naught plus D A naught. Instead of epsilon 1, there will be some slight increment in strain, epsilon 1 plus D epsilon 1 power n exponential minus of epsilon 1 plus D epsilon 1. Okay. This is the equation that we can frame for load requirement with respect to epsilon 1. So, now you given K, A naught, n, and how much imperfection you have here. Okay. So, you can get a graph between epsilon 1 versus P for the entire strip. Okay. So, now what we are going to do is we are going to discuss a situation how these two regions going to behave, okay, when you give deformation to it. Okay. So, what we are going to say is the imperfect region is actually a weaker region, correct. So, this imperfect region is actually a weaker region, and it is sensible to know that your failure is going to happen in this particular location, which we can understand that, and since it is going to happen, so I am going to simply say that epsilon 1 is equal to n, 1 star is equal to n, or epsilon 1 is equal to n for instability to develop in a location, right. So, now if this is going to happen in the imperfect region, I can simply say epsilon 1 plus d epsilon 1 will be equal to n, okay, which is what I am writing here. The imperfection will reach a maximum load. Why? Because it is weaker, okay, when the strain is epsilon 1 plus d epsilon 1 is equal to n. Same equation only, we are going to add this part. Why? Because imperfection is actually going to have a larger strains here when compared to the uniform region. Okay. So, now if this is the situation, whenever this is going to happen, there will be one particular load that will be reached. Now, at this particular load, okay, what will happen to the uniform region? If you see, uniform region would have reached some strain, let us call it as epsilon 1 u, that is called as a uniform strain epsilon 1, that will be of course less than n, okay, which is the maximum uniform strain you can have in the entire strip, okay, which is the maximum uniform strain you can have in the entire strip, okay, which is actually, the situation is actually drawn in this particular figure. So, this figure is our usual P versus epsilon 1, okay, which is nothing but with respect to your uniform region. Same graph has got P versus epsilon 1 plus d epsilon 1 also, which is for the imperfect region, and there are two curves, one is a blue one, uniform region, other one is the imperfect one, red region. So, that means what? We are going to pick up, somehow we are going to monitor load in these two locations. We are going to monitor load in these two locations separately. Material is same. So, that is one important thing. This your uniform region and imperfect region has got same material. That is why you are going to have same properties, K, N, all are going to remain same in both the locations. Material is same. Only thing, there is a imperfection at the center. You can imagine like that. So, we are going to have load versus strain for uniform region and load versus strain for imperfect region, and this is the way it looks like. And you will see that since the imperfection is going to dominate deformation, so we expect this F, which is nothing but maximum load. I have drawn here, this is the level of maximum load. When this F is reached in red color portion, you will see that this fellow will be satisfied, this equation is satisfied, d epsilon 1 plus d epsilon 1 will be equal to n. Okay. So, now when F is reached, I was telling that when F is reached, you will see the situation in the uniform region, it will go to G, okay. It will reach a point G, and G is quantified by epsilon 1 u, which will be actually less than n. This fellow would be less than n, and this is the maximum uniform strain you can have in the entire sample, okay. So, now what will happen is this uniform region cannot strain beyond G, okay. If at all it has to happen, it will happen only if you give a larger load in imperfect region more than F. Okay. If you give more than F, then only the uniform region can strain beyond G. Okay. That is what I have written here. The uniform region cannot strain beyond point G as it requires a higher load that can be transmitted by the imperfection, which is not going to happen here because we fixed maximum load happens at F when you speak about imperfection. Okay. Now, we have only one imperfect region. So, now you can imagine that there are several imperfect regions like this. Okay. This is number 1, let us say there could be another imperfection 2, 3, 4 like that. So, out of these 4 imperfect regions, okay, other than uniform region, there will be one imperfect region which is going to be severe in nature. Okay. There is going to be one imperfect region which is going to be the weakest, and that is actually going to dominate the entire deformation. Okay. And that is going to dominate the entire deformation, and you will see that you are going to have a localized deformation in that particular imperfection, and that is going to govern the entire load requirement when you do deformation. So, I am going to call that imperfection which is weakest is actually called as I am going to call that as a greatest imperfection, becomes a focal point, okay, reaching maximum load capacity, causing concentrated deformation in the neck, while the uniform region unloads elastically as the load decreases. Uniform region, if you see that the load actually when it is decreasing, it is going to elastically deform, and this is the entire situation that is going to happen in these locations. So, now what will happen? If the test is continued beyond maximum load P max, only the imperfection will deform and it will do under the falling load, the load will decrease like this. Okay. This is what will happen in the entire strip. Okay. So, now you can imagine, though we are saying that here it is an imperfection, you are going to introduce all those things, this region itself can be referred as a necked region. You can imagine that this as a necked region. Okay. You can imagine, because we know that this is what is going to have instability or neck. So, now you can simply compare what is going to happen in the necked region and in the uniform region. Okay. When you are comparing imperfect region and uniform region, you can as well compare what is going to happen in the neck region and in the neighboring region. Okay. This is what will happen. Okay. So, now the question is the difference between maximum strain in the uniform region of an imperfect strip and the strain epsilon 1 n at the maximum load in a perfect strip can be found from by following any material law, sigma is equal to k epsilon power n. Okay. So, for that we are going to use our previous equation, P is equal to k a naught epsilon 1 power n exponential minus epsilon 1. This is for uniform region, and this entire part is for perfect region. So, now what I am going to do is I am going to replace this part by n and this part by n, and this epsilon 1 I am going to keep it as epsilon u as per my this one, right. Epsilon 1 plus d epsilon 1 would be n. If that is the case, in the imperfect region F is reached. At that time, if you see what is going to happen in G or in the uniform region is nothing but epsilon 1 u, which will be less than n. So, epsilon 1 is nothing but epsilon 1 u here. Here epsilon 1 is nothing but epsilon 1 plus d epsilon 1, which will be equal to n. Okay. So, if I replace epsilon 1 here by epsilon u and epsilon 1 plus d epsilon 1 by n here, okay, you can follow some steps, and finally, I will get a simple equation like this: epsilon u by n power n exponential n minus epsilon u is equal to 1 plus d a naught by a naught. Okay. And you will see that I have also drawn this particular figure, which will be easy for you to understand. The same figure which I have referred before in perfect strip. okay, and real strip, if you compare these two, real strip is going to have sudden fall in load, okay, rapid decrement in load, okay, and this is your epsilon u, and the total strain is this actually by denoted by epsilon t, okay. This total strain is actually governed by the real strip situation rather than a perfect strip situation. That is what is given here. And anyway, we will come back to this particular equation. Okay, in this equation, if you see this n minus epsilon u, n minus epsilon u, what is n? N is nothing but epsilon 1 plus d epsilon 1. That is the strain that you have in the neck region or imperfect region, okay, when maximum load is going to happen, is going to be reached, okay, minus epsilon u. At that particular situation, what is the principal strain in the uniform region? This difference actually, okay, these are all going to be small quantities. Of course, this depends on your what is the imperfection level, okay, dA naught by A naught. That is why I am saying this dA naught by A naught is going to be a small quantity, okay. You can refer this. I have just mentioned here, this is 2 mm and T is 1.999 mm. So, you can get A from this and A from this area of cross section. What is it? Okay. A for uniform region you can get, A for imperfect region you can get. These are all actually, if you get dA naught by A naught, it is going to be a small quantity. It is going to be a small quantity. Okay. N minus epsilon u also is going to be a small quantity, but it depends on how severe is your change in area of cross section. Okay. So, now what you can do is you can do some simple mathematical calculations. You can expand this, okay, this part, series expansion you can do, and this is available in resources. Finally, I will get into one particular equation, okay, which is nothing but this part, n minus epsilon u, which is what we want. N minus epsilon u in this particular graph is this distance minus epsilon u. So, what is the difference in strain, okay, between the necked region and outside region, okay? N minus epsilon u, okay, is given by such a small equation, easy equation, square root of minus n dA naught by A naught. Here you will say that the equation tells us that the difference between maximum strain in the uniform region and n, okay, maximum strain in the uniform region. Maximum strain in the uniform region is nothing but epsilon u, and n is nothing but the strain available in the neck region or in the imperfect region. Okay, it depends on actually n value of the material and your change in area of cross section. How severe is your imperfection? Okay. So, this dA naught or the thickness imperfection you have in this particular figure, you can see this thickness imperfection you have in this particular material, in this particular figure. Okay. So, this can be actually adjusted, okay, such that the entire behavior of material is going to closely resemble that of the practical data. Okay. So, theoretically you can assume let us say dA naught as one particular value, and you can compare, okay, with respect to the real test piece data, okay, and you can little bit adjust this dA naught or the difference in thickness, okay, such that the outputs can match, which will also tell you how much of imperfection you can take for one particular material. So, this equation is going to be very, very important for us, okay, and this will give you an idea how a real test piece is going to behave when you do tensile test. Okay. So, again there are two quantities in this. The difference actually depends on one material parameter n, okay, which is nothing but your strain hardening exponent. Okay, this is one material property, and your A naught or dA naught is actually a geometrical one that you pick up. Geometrical one you pick up. Okay. So, now just to understand the significance of this particular equation, okay, this problem I have given. Okay. So, this problem, what is this problem? This problem is, so the length, width and thickness of the parallel reduced section of a tensile test piece are given as 100 mm, 12.5 mm and 0.8 mm. Okay. So, you have a test piece and there is a rectangular region, let us say gauge length, you can say this is 100 mm, this is 12.5 mm, okay, and its thickness is actually given as 0.8 mm. Thickness is given as 0.8 mm. Okay, and the material follow this particular strain hardening law. Sigma 1 is equal to 700, epsilon 1 power 0.22, and 700 is nothing but K, which is in megapascal. Okay. And what is also given is in a small length, the width is 0.05 mm less than the other locations. That means, okay, so what I am going to do is I am going to have, let us say this is my initial strip, and at one particular location I will see that there is a small change in width actually. Small location I will see a small change in width, small change in width. So, in this particular figure I am referring here, this particular figure which I already introduced, there is a small change in thickness we said. This is T and this fellow is actually less than T, right. Instead of that, what they are saying is in this problem there is a small change in width. Situation remains same, that is also an imperfection. That is also an imperfection, and that region where your width is less is going to be a weaker region, right. So, that is the only difference here. So, how much difference? The width is 0.05 mm less. So, this will directly give you dA naught. So, now what is the question? Question is estimate the strain in uniform region of test piece after the strip has been tested to fracture. So, when you deform the sheet, it will reach fracture failure. At that particular stage, what is the strain in uniform region? That means you have to get epsilon u, epsilon u. Okay. So, simple calculations you can do. So, initial area of cross section, that is in the uniform region, is you can say 0.8 into 12.5, okay, which is about 10 mm square you can get, and dA naught you can directly from this. Width is 0.05 mm less, okay. So, you can say 0.8 into thickness remains same, this thickness is going to remain same, okay, only width is reduced in this particular problem. So, I can say 0.8 into 0.05 would be 0.04 mm square is dA naught. So, dA naught by A naught is nothing but minus 0.004. It is a negative quantity. So, 0.004. So, I can straight away take this particular equation which I derived just now, n minus epsilon u is about square root of minus n dA naught by A naught. So, n is already given here 0.22 minus epsilon u we have to get square root minus 0.22 into this one, okay. A naught by A naught is this much. So, if you calculate it is 0.003, and if you get epsilon u from this 0.03 minus 0.22 0.19. So, it will become plus. So, epsilon u is equal to 0.19. So, now the interpretation is if there is no imperfection, if there is no imperfection, if the material is perfect, there is no imperfection at all, then as per our previous theory your epsilon 1 would be equal to n, which is nothing but 0.22, or you can call this a epsilon 1 star, okay. This is nothing but your epsilon u only when there is no imperfection, right. Now, this 0.22 has become 0.19 because you are putting an imperfection, because you are having an imperfection of such a small value 0.05 mm. Okay. So, you can get this difference, percentage difference, isn't it? So, what is the difference in this value you can get? Okay. So, you can see that there is about 13.5% decrement in uniform strain, okay, when you compare this with this, because you are putting in a small imperfection, very small, you see that 0.05 mm, okay. So, width of 12.5 mm, in place of that the one small region is there where you have a reduction in width of 0.05 mm. Accordingly, there is a small change in area of cross section dA naught, okay, which is like saying similar to what I said before, which is like saying, okay, here you have a thickness of 2 mm and here you have small thickness change 1.999, 2 minus 1.999, that is such a small change in thickness. Okay. If you see that such a small change in width, you are going to have a 13.5% decrement in uniform strain due to a small defect of the order of 0.05 mm width change. Okay. So, you can see that the uniform strain has decreased by about 13.5% if you put a small imperfection of this order. Now, you can imagine that how such a small imperfection is going to play a big role in determining the uniform strain, or you can say limiting strain or instability stage. Okay. So, if you do not consider this imperfection, then you would end up in actually telling people that your material is going to fail when strain is actually 0.22, which is actually not true. It is going to fail at a strain of 0.19. Okay. So, we will stop here and then we will continue in the next session.